Hello, in this video we will solve Natas 28 of the OverTheWire series, Natas series. So when you open the website, you can see that it shows a WAC computer job database. The database part here gives us a hint that SQL might be involved and we'll get a chance to put in an SQL injection. But let's see around the website. So there's a search option. If you just enter anything in the search and press search, you can see that it gives random jokes about whatever you search. It just contains the letter, not anything more than that. But what you can see is that every time you search a letter, the jokes are randomized. It is not that if you search the same thing, you will get the same results. The jokes change, but the limit of the jokes is always 3. We cannot see the source code as it has been given that they are currently out of service. So if you put in a search, you can see that the URL changes and there is a query in the URL. This again gives us some hint that from URL we can learn more about this particular CTF. Now if you change a part of the query, let's say anything, you will notice that it gives us an error that trying to access arrays offset of type bool in a line, 0 padding found instead of PKC7 #7 padding. So from this you can learn that a block cipher has been used because PKC7 is generally used in a block cipher. So now we know that the query is crypted and we have to do something about it. But we do know that a block cipher has been used instead of a stream cipher. A block cipher is one that just uses a proper way anyway to encode the data. But if you input the same data multiple times, the encoding is similar. Instead of a stream cipher, in a stream cipher, it chains up the encryption. So if you input the same data multiple times, the number of times you input the data and what was before the data changes how the data is getting encrypted. So if we want to learn more about the block cipher, we will need to put in multiple queries. So initially we will just brute force it to find multiple queries. To brute forces, the code required is, so we will put in the URL, which is Natas 28. We will request a session, put in the password, take a sample string, and initially we will increase the query by A. That is, we will brute force with a string containing initially A, then AA, then AAA, and we will like to observe the changes in the URL that we can see. But we'll start with A and we'll go till 32 instances of A. So we'll clear this up and then we will run the Python script. As you can see, the Python script constantly gives us output. So to see more of about the Python script, first we take the data as we will input the sample into the query. Then I'll just stop it for once. Then we will take the response we will post the data and store the response in R. Then we will make a variable cipher that splits the data on query equal to. If we do not do it, we will see that the URL natas 28 / query equal to appears in front of the payload, which we do not need to see. Then after it, we will parse the cipher and we print the cipher. So what we can easily observe is that there is a jump in a cipher from the 12th to the 13th character. And there is a lot of encoding involved. So this we have seen in previous many CTFs that a common encoding is base 64 encoding. So to understand it better and to show it better, we break down it to the base 64 encoding then encode it to UTF-8, and from UTF-8 we de-encode it using hex. This requires a bit of intuition, but it helps us in showing the data properly. Then we break down the data into blocks of 32. The 32 part we did because if you see that from 12 to 13, this increase can be shown by the 32 point. So this will help us in breaking down the query better. We will again clear the terminal and run the script. You will see that initially the first line and the second line in every query is same. So we know that this part is just padding and we do not need to care about it. The third line is constantly changing, but if you see multiple queries, after we increase the number of A's, you will notice that from the 10th query onwards, the third line starts remaining constant as well. And you will again also that we observed before that from 12th to 13th, there is an increase in a line. So we will first note that there is a first increase in line at 12th. Then if we further see the queries below, we can see that there is again an increase in line from 28 to 29 characters. This is 1, 2, 3, 4, 5, 6 lines. 1, 2, 3, 4, 5, 6, 7 lines. Yeah. So there is the first increase at 12 characters and the second increase is at 28 characters. So 28 minus 12, 16. So now we know that the encryption has a block size of 16. So we have done the first step of finding out the block size. Now we need to find the offset. So what offset is basically what we just learned here is that there are some padding before the query, and the padding is of 2 lines. We do not need to change it. We should not change it because if we change it, it will show us an error. Then in the third line, the query begins to start. But in the third line, it might be that there is one X, and from then on, it's our queries, any space. And after that, there is the footer, which is again whatever. If the size exceeds this size, then it goes into the next line, and the next line is our query too. And at the end of the next line, there again might be a footer involved. So what we need to know is find out this offset, because it is not necessarily one. There might be multiple characters that we do not know. So for finding out this offset, we can see that we observed that from 10 characters onwards, the third line started remaining constant as well. Also, the first new character was at 12th line. So this gives us an idea that the offset might have 4 characters, and the third line might contain AAA, gets completely filled, then goes into the next line. It might skip some characters. So to check this, what we can do is we can take multiple different queries and find out a proper offset. And you will find out that after 10, the offset changes. But there is also another point, because we are trying to add a SQL injection, which often uses special characters such as comma, backtick, so that we can end the initial query and add our payload, or a backslash, or maybe a double tick. But if we take a different query, one that just involves, let's say, 10 spaces and then a backtick, you will notice that the query is encoded completely differently. So we will again clear the terminal and run the Python script. You will notice that the query is getting encrypted in a different way as compared to the ACE query. To show this better, let's just I don't know, make 9 spaces and then a backtick, then run it again. So it again changes. Let us take 11 spaces and then a backtick. We will again get 2D94 and then F01, because again, as we showed initially, there are some offsets, and after it there are spaces. So after 10 spaces, this becomes constant, because initially we input 10 spaces. The third line we got was 2D94C. What you will see, which is similar to this, and whenever we input this back comma, you will again notice that the third line changes and the fourth line changes as well with 10th and 11th. So from this we can find out that there is a filter on certain special characters, such as a tick, a normal backtick, a double closing quotes, or a slash, because this extra line that is being added, if you notice initially, there are 6 lines just in the 11th part of the comma. That means there are some special characters added to annotate it and to filter out an SQL injection. Because unless there was a 12 to 13 character difference, it would not change. But here the number of lines increased in only from 10 to 11. So we know that there is a filter. So what we can do to skip a filter is that we know that there are initial paddings involved. We will not touch the paddings, obviously, because we need to show that the encryption has been done properly. Then there are offsets, after which there are 10 values, and after that there are footers. So what we will try to do is we will take a baseline case being one that contains 10 spaces in the third line, because if we enter anything else after the 10 spaces, it will get added. And as you saw in the brute force, the fourth line becomes constant after 16 characters, and then on it remains constant. This shows us that the fourth line is completely our query. So we'll add our SQL injection in the fourth line. Okay, maybe it overflows into the fifth line, more SQL. But that will not be a problem, because it will still have the header that we will get from our generalized base case, and the footer that again we got from our generalized base case, and it will run the SQL query. There will not be any annotation as well, because let's say if we input a backtick, and to filter out the backtick, it put in an annotation of a backslash. If we had input the query, it would have got filtered out. But since we are making the complete encryption by ourselves and inputting the query, there will be no more filtering, and our SQL injection will run. So to do this, we have used the following Python script. Let's just comment this part. We'll use the following Python script. First, we will take the data containing a query of 10 spaces, as I showed initially, so that we'll get our base case containing the footer, padding, and the offset. We will take the response, parse it, encode it. Then we will take the first 3 lines of it as the header that will still need to be in our SQL injection encrypted in our encrypted SQL injection. The footer will be 48 onwards, the fourth line onwards, which will again be our footer. Then we will generate our SQL injection into the encrypted form. To do this, we will take 9 spaces before the SQL injection. Then we will add union all select password from users. This is a payload that what merges two tables. So union basically merges any two tables, and union all just merges all the tables present in the database. And then from the table containing column, then we select password from the table users. So what this payload basically does is it takes in all the tables, and as we have previously observed in the Natas, there is always a table users containing a field passwords that usually tells us about the password of the next level. So we are hoping that the password for Natas 29 will be present in it. You can find this out by inputting some different command. Let's say you can add union all select describe to get the name of the tables, then you can get the name of the columns, and then further on you can do the query. But since all previous Natas had a similar table database, we can try this on initially. Then we'll find out the number of blocks that will be in our SQL injection. And then we will finally make our final cipher. To do this, we have our encrypted path exploit. We will add header and footer before and after the encrypted exploit. Then we will again encode the final cipher. We know our search URL. We will take the response from the get function, put in the query, and then we will use print function to read our response. So we will run this Python script. Here we'll wait for a bit because the response time may increase depending on the time it takes to read the response. As you can see, this is Natas back computer joke database, and here we have our password for Natas 29. So as you can see, we have solved Natas 28 and we have our